Okay, so we are continuing from the last time, and the topic that we are interested in this lecture is limit cycles. We touched upon it briefly when we did the van der Waals oscillator. We are going to look at it again. So this is once again index theory and limit cycles. We finally come to limit cycles. Okay, so limit cycles are isolated closed trajectories by isolated I mean that the neighboring trajectories are not closed. So as an example of a limit cycle, I can have a stable limit cycle which is to say this is my limit cycle and any orbit inside goes to this limit cycle, and from outside we spiral down. So whether or not we are outside this region defined by the closed limit cycle or inside, we hit the limit cycle. The second example can be an unstable limit cycle where basically this is the point and we are going away from the limit cycle, or if we are outside we spiral outwards. So this is an unstable limit cycle. And as you've guessed, we can have half stable cycles, which is to say I have a limit cycle and the interior of the limit cycle, all trajectories converge to the limit cycle, but outside it spirals out. So that's a half stable limit cycle. Limit cycles occur quite ubiquitously in nature. So the examples of limit cycle heart beating, body temperature, feedback control systems, so heart beating, if the heart is beating too slow, it will try to go to its natural state. If heart is beating too fast, it will try to again slow down. Similarly with body temperature, they try to naturally regulate and converge to a periodic trajectory. Feedback control systems, well, body itself is an example of a feedback control system with so many things, the hormones, the breath, the body temperature, everything regulating itself. They can occur in mechanical vibrations. Chemical oscillations, and various other examples. So the question is, can linear systems have limit cycles? Think about it. I have a linear system. Is the matrix. So notice that one property of the linear systems is that if x equals to xt is a solution, then x equals to c xt is also a solution to the same equation. So it's true that the linear systems can have closed orbits like the harmonic oscillator, but not limit cycles, because limit cycle, remember, is an isolated trajectory. But for linear systems, we'll have a lot of closed orbits occurring, infinite of them actually occurring. So this is closed orbits, yes, but not a limit cycle. In some sense, limit cycles are are more robust. Limit cycles need nonlinear systems, and are more robust. So that was just defining limit cycles. We'll come to it soon. So I ask you a question. I give you a phase space. Is there a way to rule out closed orbits? We touched upon it very briefly in the previous lecture, but that was just using index theory. For example, using index theory, we learned that the closed orbits in a plane must enclose fixed points whose indices add up to 1. That was our criteria. Is there anything else we can do? So there's something else called as the Dulux criterion, which is to say, if I have a vector field that is smooth in a plane, and imagine a region that is simply connected. So this is a region R, that's a simply connected region in a plane. So by simply connected, I mean that I can keep shrinking it and I can close. I can keep shrinking the any closed loop without leaving the region. So if there's a closed loop, I can keep shrinking it, and all the time I'll be on the region. So for example, let's say there's a hole here. Now this is not a simply connected region, not simply connected. So what's my definition of a simply connected? You can shrink a closed loop without leaving the region. Simply connected. So Dulac's criterion, what does it say? So it deals with a smooth vector field in a simply connected region, and it says is that if there exists a smooth function gx such that the divergence of gx dot, this vector field, has one sign, the same sign, either positive or negative, in the simply connected region R, then there does not exist, or we can rule out closed orbits. So Dulac's criterion deals with our smooth vector field, a simply connected region, and it says that if I can find a smooth function gx such that divergence of gx dot has one sign in R, either positive or negative, it's the same sign, then there cannot exist closed orbits. We can rule it out. So as an example, I have the vector field these guys show that this has no closed orbits in the open first quadrant. Remember, this is our same rabbits versus sheep problem. No, actually it's not the rabbits versus sheep problem. What the heck, doesn't matter. First quadrant. So by first quadrant I mean x is greater than 0, y greater than 0. So I have replacement y, x. So the solution is, of course there is a trick to finding some g, but let's say I can find the g. Let's try this g. G is 1 over xy. What do I get? The divergence of the vector field gx dot is partial derivative with respect to x, gx dot, plus partial derivative with respect to y. That's the definition of divergence. I'm just plugging in this guy, and this gives me x of 2 minus x minus y divided by y. just that this x cancels when I go, and the partial with respect to y, 4x minus x square minus 3 divided by x. So this guy goes away. This guy gives me minus 1 over y. Now minus 1 over y in the first quadrant is strictly negative. In the concerned region, and therefore according to the Dulac criterion there are no closed orbits in this region. Well, of course, the whole challenge, the challenge is to lies in picking the right function. How do we get the intuition G? It's hard to get G, but try G equals to 1. Maybe it will work. I don't know. So what's the proof? How do we go about proving? Proof of Dulac's criterion. So we go through this proof by contradiction. So assume there is a closed orbit. I have the region R. I have a closed orbit. And what do I have? I apply the integral, the surface integral of the divergence of this vector field with some G, and I apply the divergence theorem in 2 dimensions. 2 dimensions divergence theorem. Which gives me something integrated over the surface is a line integral of the same vector field over here. Okay. And by the way, the dl in this case points out normally. So my divergence theorem was some vector field integrated over the volume. Remember, that was equals to the same area, the surface integral dot dA, and by convention I take the area to be piercing out. So this is how we derived the Gauss law, remember. So this is as an aside. So if I have an area, so I am calculating the divergence of this guy over the entire volume, and this was equals to the surface integral V dot dA, where the dA is always infinitesimal area pointing out. In the same vein, I have the dl pointing out. So what do you think is this quantity calculated over the curve closing the surface in a two-dimension version of the divergence theorem. Well, x dot is the trajectory, and this is always normal to the trajectory. So this goes to 0. However, if you look at LHS, so RHS is 0. LHS, because we demand that we have found one G with the same sign in the entire region, this is non-zero. It has the same sign, and a quantity with the same sign is integrated over the entire region. This is strictly not zero. So then we have a contradiction. Just write it down. The divergence of G dot has the same sign throughout it. So we started with the assumption that there exists a closed orbit, so therefore one cannot have a closed orbit. As another example, we take the vector field. Try G is e to the power minus 2x, and I'll find that when I take the divergence of G times the vector field, I get and this comes out to be, which is always negative. So therefore I can conclude even in this example, because I have been able to find such a G, there are no closed orbits. So till now we have been, just a second, I'll be back. Sorry about that. So till now we have been concerned with the ruling out closed orbits. Now we take a different flavor and we say, what guarantees proof of the existence of a closed orbit? So let's study that in 2 dimensions. So what's happening? Let's say I have a bounded region. It need not be simply connected, it is just a bound region. And I have a smooth vector field, nothing hanky-panky is going on. And I don't have any fixed points. So this was the bounded region, this is my entire region. And I have no fixed points in the region. And I can also show that there exists a trap trajectory T. I can find a trajectory, trap trajectory T. By that I mean the trajectory is in this region R. From some initial time to infinity. So I have these conditions. I have a bounded region and it's a smooth vector field. I don't have any fixed points in the region, so that the trap trajectory cannot sink to a fixed point. So if I can trap a trajectory and I can guarantee it's till infinite time, then you can intuitively guess it has to go on a closed orbit. Then this implies that such trajectories approach a closed orbit. So I'll just write down the condition. This was my condition number 4. I had a condition, of course, I'm dealing with bounded regions in 2D, smooth vector fields. And of course, no fixed points in region. Region R. And then if I can find a trap trajectory, then I'm guaranteed a closed orbit, because these trajectories eventually wind up on a closed orbit. So either T itself, if I locate a fixed closed trajectory, T is a closed trajectory, or T spirals towards a closed trajectory, eventually as T goes to. So either way, there is a closed trajectory in the region R. So I had the region, this was my region, and then that's it. This is a trap trajectory. Eventually it will go to a closed orbit within this region. So, I mean, this is intuitively obvious. What else can happen in a plane? I give you a bounded region and I say the trajectory which I have locked in on doesn't leave that bounded region, it is trapped. Eventually, it has to go on a periodic orbit. So, what's the standard strategy? For applying this theorem is to find an annulus is like a, uh, this sort of a region is annulus such that the vector field points into the annulus or the ring on its boundaries. Suppose I am able to find this and I can show that the vector field is always pointing inwards, and over here the invert is going to be here. So what will happen? The trajectory is going to reach, it will get a push, it will be here, it reaches here, it will get a push, it will go here. So the trajectory is guaranteed to be trapped, and eventually I am going to home down on a limit cycle. So these arrows or the behavior of the vector field on the boundary ensures trajectories are trapped. So we'll look at the examples of this thing. We won't go into proof, but let's go to the examples of. By the way, this is called as a very important theorem in dynamical systems. So this is called as the Poincaré-Bendixson theorem. So essentially, let's say I have a simple example. R dot it's a nonlinear system. So let's first see the easy case when mu is equals to 0. Then I have R dot is and I'm able to decouple these guys. So for this particular system, I have the standard form. I have a stable, unstable point, and then I have a stable point. And how does it look in the phase plane? In the phase plane, I have some. So over here, this occurs at 1. So I have a closed orbit, and any trajectory, I just make the closed orbit by So these guys spiral in, and these guys spiral out. And I have a closed orbit. Now let's make things more interesting by considering mu not equals to 0 in the above example. So I'll again write down and I can ask the same question. Does the closed orbit still exist?